All right, let's continue to talk about h of z and h of s, comparing these two continuous time and discrete time kind of ways to analyze the system. First of all, let's consider the frequency response. H for a discrete time system. H e to the j omega is the sum x of x, not x, h of n e to the minus j omega n. For some systems, this does not converge. For example, if the system has a response that's the unit step function, you can show that this just doesn't converge, so it doesn't even exist, doesn't have a frequency response. But sometimes we still want to analyze systems like this. So what do? And the common way to approach this is to stick in what's called a convergence factor. And the convergence factor is something we stick into this sum to force this infinite sum to converge. And here's how it works. So instead of e to the j omega, we're going to plug in r e to the j omega. And originally r is 1, but now we're going to see what values of r make this frequency response converge. And I'm going to go ahead and plug in unit step function, and it goes from 0 to infinity. It's a unit step function. And then we're going to have r e to the j omega. Now this whole combination is raised to the minus n power. Okay, so those are the exact same things, except now I've got this convergence factor in there. And I claim that there's some value of r that will make this converge. For example, if we let r equal to 2, for example, then we get the sum of h of n is just the unit step function, so that's just 1, and we've got r to the minus n e to the minus j omega n. So everything's the same, except now we've got this convergence factor. And as you can look by inspection, as n gets really large, 2 to the minus n is going to die off to 0, because 2 to the minus 1 is 1/2, and if you square it or cube it, it keeps getting smaller and smaller, and this thing will converge. And what we do is we package this up. We package this up with e to the j omega and r. We just call it z. So r is the convergence factor, and this thing converges. In our little example, converges as long as the magnitude of z is, which is equal to r, right, is greater than 1, and we call that the region of convergence. All right, so we get two benefits out of this. If we let r equal to 1, we still get the frequency response, just like always. And the other thing is, by looking at what values of r cause this to converge, we get some information about stability. So the upshot is that now that's where we get the z transform. Oops, keep wanting to write x there. H of n, z to the minus n. Okay, so that's the z transform. It includes within it the frequency response when we set the magnitude equal to 1, and it also includes the ability for us to look at stability issues with respect to this system. Okay, and note that this thing is in polar coordinates. It's polar coordinates, and you only use polar coordinates when there's some kind of circular symmetry, and we found that out. There's lots of circular symmetry here. This e to the j omega is periodic every 2 pi, just like a circle. So polar coordinates are the best way to describe discrete time systems. Well, let's look at continuous time systems. Same sort of thing happens. We have h of s. It's the integral h of t, e to the minus st, where s is equal to sigma plus j omega. Well, guess what sigma is? Sigma is related to this convergence factor. Let's see, I need the dt in there. Let's expand this out. H of t, e to the minus sigma t, e to the minus j omega t dt. So we can see there that this part is related to the frequency response. So, right, when we just have this term, without that term we get the discrete or the continuous time Fourier transform, but this term is going to be the convergence factor. So when we let sigma equal to 0, this thing is equal to 1 and we get the frequency response. But by looking at what values of sigma are required to cause convergence of this integral, we find out about stability of the system. We tend to call this complex frequency. It's got actual frequency, and then sigma allows it to be to have various convergence values. Okay. Similarly, up here we tend to call z complex frequency for discrete time systems. Okay. All right. Now, since s equals sigma plus j omega has no circular symmetry, there's no symmetry, there's no periodicity involved here, we leave this in rectangular coordinates. It's awfully difficult to describe things that have no circular symmetry using polar coordinates, and vice versa. So because of the fact that time in discrete time, n, is always an integer and results in circular symmetry, but in continuous time there is no periodicity, so we use rectangular coordinates to describe the frequency variable here. And just remember that whenever sigma is equal to 0, we can always get the discrete time Fourier transform. We get the frequency response for continuous systems. So let me draw a little table here. Continuous time systems on the left, discrete time systems on the right, and just do a little comparison. So this is stuff that we should know. First of all, let's talk about frequency response. Okay, to get frequency response in continuous time systems, we let s equal j omega, where omega goes from minus infinity to infinity. For discrete time systems, we let z equal e to the j omega. Okay, that gives us our periodic kind of thing, because this is a vector that goes around in a circle. Minus pi, we generally look at the frequency omega in the range minus pi to pi, because outside of that range everything repeats and repeats over and over again. So this is a range where everything's kind of unique and unambiguous. The frequency axis is the j omega axis. Over here, the frequency axis is the unit circle. Okay, So this is the unit circle, and this is a straight line. What else? So that's a comparison. The frequency axis is a circle. Here it's the j omega axis. What about stable poles? Stable poles for continuous time is the left half plane. Remember that? And that just means that the real part of any pole, of the kth pole, for example, has to be less than 0. That's the left half plane pole, left half plane for stability. So there's the S-plane. Over here, we need to have the poles, if they're stable, have to be less than 1. So they have to be inside the unit circle. Okay, so we've got a unit circle in the z-plane. Stable poles are inside the unit circle. Well, if you think about it, this is the j omega axis, right? J omega axis. This is the frequency axis for continuous time systems, and this is the frequency axis for discrete time systems. There are stable poles on the left half plane. There are stable poles interior of the circle. What I want you to do is start imagining that this frequency axis, the j omega axis, maps to, when we go to from continuous time through a digital analog to digital converter, this frequency axis wraps around this circle. Frequency axis, frequency axis. So you can imagine that this frequency axis wraps around this, and this entire left half plane in the S-plane maps into the interior of this unit circle. So all of infinity, okay, on the left half plane maps into this one little circle, and so we get some ambiguity. Obviously, this infinitely long frequency axis wraps around and keeps on wrapping forever around this unit circle.